Hi, I am Dr. Meghabriti Pramanik, Associate Professor of Electrical Engineering Department, Haldia Institute of Technology. Today I will deliver a lecture on the Z transform. So, before going to the topic, what is Z transform and how it is applied in signal processing, at first we have to know what is Z transform basically. Basically, the Z transform is a powerful mathematical tool for analysis of linear, time invariant, discrete time systems in the frequency domain. That means if you have any signal, any type of signal, it may be continuous time or discrete time, but Z transform, what it does basically any continuous time domain signal into the discrete time, and the signals would be linear and time invariant. Okay, and whatever be the discrete time signal, it transforms the discrete time signal in the frequency domain. That means if you have any continuous time domain signal, at first you just turn it or you just convert it into the discrete time, and this discrete time will be in the frequency domain. Okay, and second point is the convolution of two time domain signal is equivalent to the multiplication of their corresponding Z transform. That means if you have any time domain signal, okay, so when you are required to make the convolution, so better to transform these signals in the Z domain, and after Z domain just multiply, so the complexity reduces. This property simplifies the analysis of the response of an LTI system to various signals. That means whenever you can say that the complexity of the convolution reduces, and you can only just multiply two signals if you transform into the Z domain. Okay, and the last point is the discrete time equivalent of the Laplace transform. That means the signal is also equivalent to the Laplace transform. That means whatever the operation is done in the Laplace transform, it is also similar to the Z transform with some difference. So the next point is the why Z transform is required. Okay, so we can say that the Z transform, why it is required. So the analysis of the discrete time systems. That means it is used for the analysis of discrete time signal and linear time invariant system in engineering fields. Next, the point is coming that the solving different equations. That means difference, it is not different, but it is the difference equation. That means you always know that when the signal is in the continuous time domain, at that time we use the different equation, but when it is in the discrete time domain, at that time we use the difference. That means one is differential equation, another one is difference equation. Differential equation is required when the signal is in the continuous time domain. Okay, and the difference equation is required when the signal is in the discrete time domain. That means when you are making the Z transform, that means in the discrete. Okay, so it simplifies the solutions of linear difference equations with constant coefficient, which are common in digital systems. You also know that in the digital signals, okay, in the digital signals, this is very much is essential. That means the difference equation, okay. So another point is the stability assessment. So also we can say that for the stability assessment, that means if you are provided any type of signal, okay, any type of signal or any type of system, then the last question may be asked that whether the signal is or system is the stable or unstable. Okay, so to know that whether the signal is stable or unstable, you have to do what? You have to do the at first you just convert the signal in the Z transform, and then there is one property, that is which is the ROC property. That means ROC, which is the region of convergence, and in the region of convergence you can locate all the poles. If the Z transform, it is the numerator, okay, and this is the denominator. So by the placement of the pole, that means in the denominator part, by placing the poles in one uh, by placing the poles, you can find out whether the system is stable or unstable. Okay, that means if you are provided the denominator section represents the poles, and if you are drawing one circle which is unity circle, okay, this is the unity circle, that means the radius is 1. Okay, or if I fix that the radius is r equals to 1, and you just place the poles. Okay, so after later on we will discuss on the causal system and non-causal system. Okay, for the causal system, okay, you will find that the ROC is outside the unit circle, okay, when the system is causal, and when the system is non-causal, then you will find that the when the system is non-causal, then you will find that the ROC, in case of ROC, okay, you will find that all the poles are within the, or the ROC will be inside the unity circle. Okay, this is for causal signal and this is for the non-causal. Okay, so from here, if you find that the any signal is causal, at that time the ROC will be outside the unity circle. At that time you will say that the signal or the system is the stable. Okay, the system is stable. And for the non-causal or anti-causal system, if you find that the region of convergence is inside the unity circle, at that time you can say that the system is stable. Okay, in that way you can assess the stability. Next point is the digital signal processing. That means right now I am discussing what are the properties or why we are using the Z transforms. Okay, so it is critical in designing and analyzing the digital filters. That means the digital filters in the continuous time domain, you cannot design particularly or specifically any type of digital filters, but if it is in the discrete time domain, or you can just convert it into the Z domain, then you can find that the drawing any type of filters is making very much easy, and it has vast application in the image processing and also in the communication. Okay, and next one, the point is coming that the conversion to frequency domain. So the next point, which refers to the conversion to the frequency domain, that means it maps discrete time domain sequence into the Z domain. That means Z domain means if you have any type of continuous type of signal, that means this type of continuous signal. Okay, that means this is the continuous signal, and you can make it in the discrete time domain signal. That means how can you discrete? That means by using the sampler. Okay, so by using the sampler, you can make the signal as discrete. Okay. So after making the signal discrete, okay, so you can use the you can use the Z transform. You can use the Z transform. Okay, Z transform. So in case of Z transform, what you are doing, you are just whatever the discrete time domain signal you are getting, okay, you are making it in the frequency domain. Okay, so the frequency analysis of the signals are very easy. So another point is the why we need the signal why we want to make the signal in the discrete time domain or frequency response rather than the using it in the time domain. So we can say that if you are using any type of signal in the time domain, we can say that, so for if the time is t equals to 0, you are taking 1 point. If it is the time is t equals to 1, you are also taking 1 point. If the time is t equals to 3, okay, I am using another color. If the time is t equals to 3, okay, t equals to 3, you are getting some point here. So but in between 0 to 1 there are many signals, in between 1 to 2 there are also many signals, in between 2 to 3, 3 to 4, in that way there are many data or many values you are getting. So if you are told to store all this data in some embedded platform or in some hardware, then you require the memory which is very high. Okay, very high memory you are required. But if this signal is transformed into the Z domain or into the frequency domain, what is its beauty? Its beauty is that if the signal is only the 50 hertz, then only by spectral analysis, okay, you are getting only one spectrum in the 50 hertz. Okay, you are getting one spectrum in the 50 hertz. So only this data, that means at 50 hertz you are getting one spectrum. Okay, so this 50 hertz frequency only stored in the embedded platform. Okay, so the conversion of the Z domain or frequency domain is more easier than the continuous time domain. Okay, later the portion which is coming, the system characterization. Okay, so the system characterization using this transfer function or mapping input the output relationship is becoming very easy. Okay, so we can say that the all these points, that means all these points we can say that the all the signals because of this, that means the DSP, conversion of frequency domain, system characterizations. Okay, and in the previous slides whatever we have discussed, we can say that the for all those things the Z transform is becoming very easy. Okay, now coming to the what is the Z transform. Okay, that means the mathematical expression for the Z transform. Basically, Z transform is the bilateral. Bilateral, why we are telling this term bilateral? Okay, we are using bilateral means what? That means in two ways. Okay, if I draw this one, that means which is, this is the origin 0, this is plus infinity. Okay, and this is, and this one is the minus infinity. Bilateral means that, okay, from 0 to plus infinity is the, if this is from 0 to plus infinity, if there is your right hand, okay, that means we can say this is the right side. Okay, this is the right side. And if you are telling that from 0 to minus infinity is one side, that means this is the left side. Okay, this is the left side. So we can say that the this Z transform holds the length or holds its limit from minus infinity to plus infinity. Okay, that's why we are using it as a, or we are telling it as a bilateral. Okay, so now coming to the point that the Z transform is equals to, what is its definition? N equals to from minus infinity to plus infinity x n z to the power minus n. Now you can say why we are using x n in that way. Okay, why we are using xn in that way? This is used xn in that way because of the discrete time property. Okay, if you are using xn in that way, okay, this is the continuous time domain expression. Okay, but when we are using xn in that way, this means that this is the discrete time signal. Okay, so now coming to the point is that summation n equals to from minus infinity to plus infinity x n z to the power minus n. Okay, where x n is the discrete time signal, z is the complex variable. Okay, and z can be written equals to z equals to r e to the power j omega. So another point is the left sided and right sided. Okay, so from here we can say that if the limit is from 0 to plus infinity, at that time we can say it as the right sided Z transform. Okay, and if the limit is coming from minus infinity to 0, okay, so that means from minus infinity to plus 0 our left side is there, so we can say it as the left sided Z transform. Okay, so coming to the next slide. Now the point is coming that the unilateral Z transform. Okay, unilateral Z transform is xz equals to from 0 to plus infinity x and z to the power minus n, which is known as unilateral. Unilateral. So also we can say that the unilateral from 0 to plus infinity, which is in the previous slide whatever we told that the from 0 to plus infinity it is right sided. Okay, so it is also called as for causal signal or causal system it is used. Okay, so similar way we are writing, if this is your 0, okay, this is your plus infinity and this is your minus infinity. Okay, so from 0 to plus infinity, this is your right side is here. Okay, or right hand is here. Okay, so this is the right sided Z transform, and this Z transform is also called the causal. Okay, causal. Okay, cause for causal signal or causal system, the right sided Z transform is present. Okay, and in the next slide, the vice versa, or we can say that the reverse of this one we can find. Okay. So, coming to the point is that whatever we have started, so now continuing this portion, that the example of right-sided exponential sequence. Okay, up to that you have done with that. That means only if it exists, if the A Z inverse mod of this one is less than 1. Okay, that means if the that means if this is the unity circle, okay, if this is the unity circle with r value, r equals to 1, okay, so because I told that in the previous lecture that the r z equals to r into e to the power j omega. Okay, so this is the value of r. Okay, so if r equals to 1, at that time the circle is becoming unity circle. Okay, so now the point is coming, what is the ROC? ROC should be a into, that means this one. Okay, a into z inverse would be less than 1. That means which should be in the unity circle, within the unity circle. Okay, so so the series will converge if this one holds. That means the mod of this one will be less than 1. So from here we can expand. If the series is expanded, then you are getting 1 divided by 1 minus a into z inverse. Okay, which is equivalent to z divided by z minus a. That means mod z greater than mod a. That means what is happening? If this is the circle, okay, that means what is the meaning of this one? That means mod z greater than a. That means if this is the unity circle, okay, if this is the unity circle, okay, and 1 and a is within that unity circle. Suppose the pole, that means this is the pole, numerator by denominator, in the denominator side represents the pole. Okay, so if the pole, so if the pole a, okay, which is within the unity circle, if I am considering it within the inside circle, that means here is the pole. Okay, so a is within the unity circle, that means mod z, that means the region of convergence will be the outside the circle. Okay, if I draw one circle with radius a, that means the ROC will be the outside the circle of a radius. Okay, that means if it is the circle with radius a, then the ROC, that means the region of convergence of this system, will be if the ROC is outside the circle whose radius is a. Okay, up to that I think that this is clear to you. Okay, so this is only for the causal signal. Okay, you also know that the for the causal signal, what will be the limit? Limit will be from 0 to plus infinity. Okay, this is the limit.